Okay, welcome back to Calculus and section 7.1, dealing with the area between curves. Now, in the first lecture for this section, we talked about how we can calculate the area between curves using vertical rectangles and being able to calculate vertical distances between curves. Unfortunately, we run into a problem in certain situations where the vertical method does not lend itself to a problem very well. As an example, in the curve that in the picture that I've drawn for you below, we have two functions. We have f of x, the parabola, and g of x, the straight line. Now, the issue with trying to use vertical distances and vertical rectangles here is that depending on where you draw your rectangle, it's going to affect what's high and what's low in the function. So if I shade in the area that we're trying to find, it's the intersected area between the parabola and the and the straight line. But again, depending on which rectangle you look at, as an example, if I were to draw a rectangle in this location and call it rectangle number 1, you notice that we do indeed have a vertical rectangle, but the issue is that the high function for that blue rectangle number 1 is the top half of the parabola. The bottom, the low function for that blue number 1 rectangle is the bottom half of the parabola. Now, you might not think that's a big deal, but if we move a little bit further to the right and look at a rectangle in this location that I'll call rectangle number 2, now the issue is we have the straight line, g, being the high function, and the bottom half of the parabola, f, being the low function. And of course, if I keep moving to the right, you'd see that that continues to be the case. And if I were to try and find the area using vertical rectangles, I'd have to do it in pieces. I'd have to do it piece-wise. I'd essentially have to split the picture at the point of intersection here. So I'll draw a heavy blue line. I'd have to split it and do it in two parts. One to the left of that blue line, where the high function would be the top half, the low function would be the bottom half of the parabola. And then to the right of that blue line, we'd have the straight line on the top and the parabola on the bottom. So we'd have to do it in pieces. All right, and even worse, the equations would have to be would be troublesome to use, would be difficult to use. So in a situation like this, we're not going to choose to use vertical rectangles. Instead, we're going to use horizontal. And therefore, we need to be able to calculate horizontal distances between curves. Just as we had done with vertical, we need to do the same thing with horizontal. And so I've drawn two curves for you, and I've identified some points on the two curves. And what I would ask you for is the distances between those 2 points. So I'll start up high. The distance between these 2 points, or these 2 points, or these 2 points. Can we calculate those distances? And if you notice, if you look closely, in each pair of points, the y values are the same, but the x's are different. So to calculate the distance, since the y's are the same, let me use my laser pointer here. Since this y value, 8, is the same as this y value, 8, then the distance between the points is just going to be the difference of the x's. So my question to you guys would be, how far is it from x equals 2 to x equals 5? And of course, you would tell me 3. Or if I do the same thing with this pair, notice that this y value is 1, this y value is 1. And therefore, the distance between the 2 points is the difference of the x's. So the distance between -5 and -3, you guys would say, is 2. And finally, the lower points here, again, the y values are the same. Y value -2, y value -2. So this distance, this horizontal distance between the points, is then going to be the difference of the x's. So again, I would just ask, if everybody was here, I would just ask you guys, hey, what's the distance between -9 and 7, and you guys would say it's 16. But again, just like with the vertical, we need to be a little more precise. How do we actually calculate those distances on a consistent basis for any kind of curves? And the key is going to be to remember a second phrase. With vertical distances, I asked you to remember the phrase high minus low. Well, when we're talking about horizontal distances, what I want you to do is remember the phrase right minus left. All right, and that's going to always give you the distance between those 2 points as a positive value. So if you look, let me select my laser pointer. If you look in this upper pair of points and look at the difference of the x's, right x minus left x, right is 5, left is 2, so 5 minus 2 is 3. And I could write that out. Anybody would like to see it? The point to the right minus the point to the left gives us the distance between. Here in the middle, these 2 points in the middle, again, the y values are the same. So the distance is going to be the x value to the right minus the x value to the left. And again, I'll write that out for you. I'll just scooch it over to the side. So this would be x value on the right minus the x value on the left. So right minus left. And -3 minus a -5 becomes +2. And for this last one, the distance between these 2 points, we're again going to think of the phrase right minus left. So the, excuse me, x value to the right minus the x value on the left. So 7 minus a -9 would get us a distance of 16. So this concept of using right minus left will always give us a positive distance. Positive distance. So vertical rectangles, we're going to remember high minus low. Horizontal distances, we're going to use right minus left. All right? Now, some situations that we're going to run into very similar to, very similar to finding areas using vertical rectangles, we can find areas using horizontal rectangles. And I've given you 3 examples of situations where we could use horizontal rectangles. So again, there's going to be, to start with, example number 1, we can have an area determined by points of intersection of 2 curves. Or in example number 2, we do not have the intersection of 2 curves, so we'll often have to be given 2 values between which we're going to find the area. So maybe we'd be given this value on the top side and this value on the bottom side, and we'd want to find the area in between. So I hope that's a familiar concept from our vertical problems. We'd be looking for that area. And just as we did with the vertical problems, we're again going to want to understand what's called a representative rectangle. Okay? And in these 2 cases, to start with, a horizontal rectangle is going to be the way to go. Because if I draw a horizontal rectangle in this first problem, no matter where I draw it, high or low, no matter where it is, high or low, the horizontal rectangle will have which curve on the right and which curve on the left. Well, on the right-hand side is going to be the parabola everywhere, and on the left-hand side everywhere it's going to be the straight line. So the horizontal rectangles, again, are going to be the way to go. In my second example, again, no matter where I draw a rectangle in, high, middle, low, anywhere you draw it, one curve always on the right-hand side, the other curve always on the left-hand side. All right, so again, horizontal rectangles are going to be a really good way to represent the area that we're trying to find. Okay, and before I get to my third example, I'd just like to point out, so that it makes sense when we start doing examples, please notice that for all of the representative rectangles that I've drawn, the lengths are horizontal. So keep in mind, we're going to be finding areas of rectangles. So areas of rectangles, of course, are lengths times widths. Please notice the lengths are horizontal, are side to side, are right to left. And the width is going to be the infinitely skinny. Remember, we're going to be adding up an infinite number of these folks. So the width is going to be infinitely skinny, but they're all infinitely skinny up and down. These are all infinitely skinny up and down, all of these. And since they're infinitely skinny up and down, that means the width part of every one of our pictures, of our rectangles, is going to be the differential. But because it's up and down, our differentials this time are going to be dy's. So the dy, that differential, is going to represent the width of every one of those rectangles. Okay? And because we're going to have dy, that means all of our functions then have to be in terms of y. Remember, the variable in your integral and the variable attached to the differential have to be the same. Now, I have drawn a third example, and let me shade the obvious region intersected by the two curves. Okay, so there's the region that we'd be trying to find the area for. But I just want you to notice that there are problems where either vertical or horizontal rectangles would work just fine. As an example, in my number 3 example here, no matter where I draw a vertical rectangle, no matter where I draw one in, you can clearly see that one curve is always high, one curve is always low. And if I switch colors here just so you can kind of see the difference, if I use yellow, I could also draw horizontal rectangles in. And no matter where you put a horizontal rectangle, one single curve is always to the right, and another curve is always the other curve is always to the left. So you wouldn't have to do anything piecewise, but you'd have the choice between either vertical or horizontal. All right, so there are going to be problems where you have the choice. Okay? So that's the idea. Overall, we can use either vertical rectangles to find area between curves or horizontal rectangles to find areas between curves. Depending on how the curves are drawn, how they intersect each other, or where the intervals are, will dictate whether you use vertical or horizontal rectangles and calculating the appropriate distances. All right? So what we're going to do, just as I did on the previous, is we're going to jog through a couple of examples. Jog through a couple of examples of situations where we can find area between two curves. Okay, so here's an example. Let's use x is equal to 3 minus y squared. Let's use y is equal to x minus 1. And on this problem, I'm not going to give you an interval, which should lead you to the idea that, hey, if there's no interval given, that means that the two curves must intersect each other. So just as we did with vertical problems, you have to get a decent picture drawn. Okay? Now the issue here on this problem is that the first equation is obviously a parabola because you have one variable raised to the first power, the other variable raised to the second power. But the issue is that it's kind of the other way around. It's not y equals, it's x equals, which means this is going to be a parabola that opens sideways. The plus 3, the positive 3, tells us that it's a parabola that starts 3 to the right. And then the negative attached to the y squared tells us that it opens left in the negative direction. All right, so just roughly would look something like that. Would be my first equation. So this would be the x equals 3 minus y squared. Now my second equation, much easier to look at, is just a plain old straight line. Y is equal to x minus 1. So a straight line that goes through negative 1 on the y-axis and has a slope of 1, so up 1 over 1. And then through those 2 points, we can draw our straight line. So that would be the straight line. Y is equal to x minus 1. And just as we demonstrated earlier, you can see that vertical rectangles would be a problem because if I drew a vertical rectangle in here, the straight line would be high, the parabola would be low, but when I get over here, the top side of the parabola is on the high and the bottom side of the parabola is on the low. Again, that would force you to do it piecewise. So instead of doing that, what we're going to do instead is calculate this area, again, which I'll shade for everybody, just so you kind of keep a visual as to what's going on. But we're going to calculate that area using horizontal rectangles, because when you use horizontal rectangles, no matter where you draw one, no matter where you draw a horizontal, the parabola is always on the right-hand side, and the straight line is always on the left-hand side. So the parabola, always on the right, here, or here, or here, and the straight line, always on the left, here, or here, or here. Okay? So then our setup to calculate the area is going to be the definite integral. So we're adding up an infinite number of rectangles. But now the phrase we're going to have in our head is not high minus low, but right minus left. So we have to decide for ourselves what function is on the right and what function is on the left. Now, before I go any further, please notice that with any of the blue representative rectangles, the infinitely skinny width is again vertical, up and down, so the differential on our integral is going to be a dy. All right, let me choose my laser pointer here so I can just point that out, or try to point that out. The differential here has got to be a dy, because the rectangles are infinitely skinny in the vertical direction. Okay? That means that my right function has to be in terms of y, and my left function has to be in terms of y, because the differential is in terms of y. Also, the limits of integration, the lower number and the upper number, have to be in terms of y. So the limits of integration will be in terms of y. The right function has to be in terms of y. The left function has to be in terms of y, because the differential is in terms of y. Everything has to match up. All of those have to match up. Okay, so to get those to match up, let's see what we can do. What function is on the right-hand side? The parabola. And how does the equation of the parabola read? 3 minus y squared. We're in good shape because that's in terms of y's. That's good. But the function that's on the left is the straight line. So you'd be tempted to say, oh, I see the equation of the straight line. That is equal to, or I'm sorry, that is y is equal to x minus 1. But we can't use x minus 1 because it has to be in terms of y. So I have to back that up and rewrite the equation. Rewrite this equation, our second equation, y is equal to x minus 1. We have to rewrite that in terms of y. So that means we need to move the negative 1 to the other side by addition. So I can replace the left equation with x is equal to y plus 1. Now you can see that the right function is in terms of y's. The left function is in terms of y's. Differential, again, still in terms of y. So y's here, y's here, y's here. The only thing we're missing now are the limits of integration, which again must be in terms of y's. So how do we find those limits? They're not given to us as an interval. So as we did in the previous example from the first lecture, what we have to do is we have to figure out where the two equations are equal. So we have to figure out where is 3 minus y squared equal to y plus 1. And where did those come from? 3 minus y squared is from the first equation. Y plus 1 is from the second equation. We have to figure out where those fellas are equal to each other. And since that's a second degree equation, what I'm going to choose to do is get 0 on one side. So I'm going to move the negative y squared to the other side by addition, leave the positive y where it's at, and move the plus 3 to the other side by subtraction. So 1 minus 3 is negative 2. And now the trinomial can be factored. Again, I just set this one up so it works out kind of nice to start with. So the numbers that multiply to get -2 and add to get +1 are +2 and -1. So when you set those equal to 0 and solve, you'll get y is equal to -2 and y is equal to +1. So if I go back up to my picture, these two curves intersect at -2, and these curves intersect at +1. Okay, so that gives us then our limits of integration. And our integral is now all set to go. We're completely ready to roll. Okay, so I'm just going to, before I integrate, simplify a little bit. I'm going to remove the parentheses. Please notice when there's a minus in the middle, remember to subtract both the y and the 1. I'll put the two numbers together. So +3 minus 1 is +2. And now I'll have to slide the screen up a bit so that I can integrate. So add 1, divide by the new, add 1, divide by the new, attach the variable of integration. And then we're going to be f-ticking from 1 down to -2. So everywhere you see a y, put in 1. And now everywhere you see a y, put in -2. But again, please remember, whenever you put in a negative, wrap it in parentheses. So this will be the opposite of -2 cubed over 3 minus -2 squared over 2 plus 2 times -2. And then we just need our calculator to start doing math. Let's see, that's 3 negatives altogether, so that's +8/3. Let's see, that would be -2 squared over 2, so that would be -2, and 2 times -2 is -4. -1/3 minus a half plus 2 is going to be +7/6. 8/3 minus 2 minus 4 is going to be -10/3. And then the two negatives make for a plus, so 7/6 plus 10/3 is 27/6, which when we cancel a 3 top and bottom reduces to 9/2. So the area between the two curves that we started with, hopefully this doesn't get too small for everybody, but the area then is +9/2 square units. All right, look okay? All right. Again, you got to adjust your brain a little bit because the rectangles are horizontal of each other. Okay? So that's going to be the end of this video lecture. The third video that's going to go along with this, with section 7.1, will be nothing but examples. So depending on where you're at, do you feel pretty comfortable? Do you need to see a few more? You can definitely watch the third video. It's going to be nothing but examples of areas between curves. So nothing new in terms of material, just examples. Okay? So hope you're having a good day. Enjoy your math, and we'll talk to you soon. Have a good day. Thanks.